What's going on, everyone? This is Devin here. Today we're looking at the plate characteristics of the ECC 83 or the 12AX7, and the context of this discussion is designing a long tail pair phase inverter. Okay, so we could borrow from a lot of different circuit topologies, put them into most any amp, and you could build your amp, power it up, and it's going to work. You know, you're going to have sound, and it may even sound pretty good, just kind of, you know, using a grab bag of long tail pair designs. But I want to talk about this from creating one from the ground up here. So we're going to assume our starting point is a source voltage of 300 volts. And since the 12AX7's plate resistance is about it's about 62.5K. So I'm actually going to use 120K plate resistor. So I'm going to double that 62.5K value. So our source voltage is 300 volts divided by 120,000 ohms equals 2.5 milliamps. So we're going to come over here. What is this? Right around here. That's going to set the slope of the load line. And you're going to see more than one load line here. So it may be kind of strange if you've never really seen this before. Got the angle of that a little bit off, but that'll be close enough for our purposes. So I want to target a difference between the grid and cathode at about, negative 1.5 volts, just a typical operating point. And so we'll slide down here and on this negative 1.5 volt line until we hit our the load line slope angle here. We hit right about there. Right around here is where we hit. And we'll find that we are going to be operating right around 1 milliamp. So this is very much standard value or standard operating current kind of stuff here. So usually we would take 1.5 volts divided by 1 milliamp to get, our 1500 ohm cathode resistor. But we can't do that. That's later. The other thing we can take a look at here is where our plate voltage is going to fall. Let's see, that's 150, 60, 70, 80. It's about 185, believe it or not. So usually we would like to bias around half of our supply voltage, but we're going to, in this hypothetical model here, we're going to say 185 volts is going to be our nominal plate voltage. So we need that number to draw our next load line. So we're going to take 180 volts, and we want 25 to 30% of our plate voltage to show up on the cathode. And you're going to get that because you have that big value tail resistor. And we're going to get to how you calculate that tail resistor. So 185 volts. I was wrong. 185 times, let's say, times 25% equals, I don't want to forget these numbers. 46, we'll just say 46.2, and 185 times 0.3 equals 55.5. So we can just split the difference and just call it 50 volts. So we're gonna target a cathode voltage of 50 volts. what we have to do with that 50 volts. So we started with on our first load line with a source voltage of 300 volts before the plate load resistor. So now we got to subtract 50 volts from the 300, which now means we're going to draw a new load line at 250 volts. So now we got to say 250 divided by 120K equals 2 milliamps, almost 2 milliamps on the nose. So still nothing crazy going on here yet. So that's our 2 milliamps. So now I'll try to do a little better job with our load line here and not get the angle all crazy. Make sure we're kind of square-ish in frame here. And this is our new load line that we get when we add 50 volts to the cathode but take it away from the source voltage. So now we have to choose a reasonable operating point. -1 volt is probably a little risky because we could run the risk of the grid swinging positive at that point. 1.5 volts, we're kind of in sort of a non-linear area. So maybe we could just, I'm going to off on the side here, 1.25 volts negative. So let's call that right there at that point. Might show up a little better right here. So we're going to come over. It's going to put us at 0.8 milliamps. 0.8 milliamps. You really can't see that right there. So 0.08, or excuse me, 0.8 milliamps. I'm sorry, not 0.08, 0.8. So we're going to take 1.25 volts and divide that by 0.0008 amps. That's going to equal actually 1500 ohm cathode resistor. But we'll have to split. We'll have to cut that in half though, because both cathodes share the same. Really, is the biasing resistor is what that is. So we're going to say we're going to need a 750 ohm resistor. Right here, this resistor right here, we're gonna call this 750 ohms. All right, right there. That's the part of the circuit we're talking about. Now we have to calculate the tail resistor. So now we have to say we had 0.0008. Now we got to double that, because that, 0.8 milliamps is just for one triode. We have double that current. So we're going to wind up with 1.6 milliamps. So we're going to take 50 volts divided by 1.6 milliamps, and that brings us to 31.25. So now things are starting to look a little more like normal. Very close standard value would be 33K. 33K. So there's not an oddball number here at all. And, you know, I'm just using 1 meg for our grid resistors here. So we got a 750 ohm, basically our bias resistor. This resistor, this 750 ohm resistor, really what it's doing is setting up that grid bias differential. So theoretically, we could possibly see, we would probably see plus 1.25 volts here at the cathode. Okay. Now, if we put our positive probe on the grid and the negative probe on the cathode, we would look at it right here and we should actually see minus 1.25 volts. If we took a reading right there at the audio grid, the input grid, and that's where we would, that's what that number is. That's where we would see that. So we're right between -1 volt and negative 1.5 volts. And there it is. That's that, trying to find something that'll show up 1.25 or negative 1.25. There it is on the load line sheet. And there it is staring you in the face with your multimeter, just to put all of this in perspective. So, and if I were to put my multimeter, the positive probe on the multimeter right here, and then the negative probe right here, I should see roughly 50 volts, right? So again, if I put my positive probe from right here and my negative probe right here and just looked at the voltage drop across that 750 ohm resistor, I'd see 1.25 volts. If I put my positive probe right here and my negative probe on the chassis ground, I would see something around 50 volts DC. So that just gives you, you know, sort of all the biasing parameters and all that kind of thing. So we'll just do a quick recap and call it a day here. So the reason we had to start with a conventional load line, in as much as I understood the write-up from Aiken amplifiers, we had to start with a regular load line, with a typical load line configuration, to get our initial plate voltage of 185. I had to multiply that by somewhere between 25 to 30% to come up with a nominal cathode voltage of 50 volts. Let's say we're at 27.5% of the plate voltage. You know, we had to have something to base our cathode voltage on, something logical, something that would make sense, and something that is really born straight out of the load line numbers here. So we subtracted that 50 volts we want on the cathode. We subtracted that from our initial source voltage of 300 volts, and we shifted that over to 250 volts, right? And replotted another 120K plate load resistor load line here. Then we found as reasonable of a bias point as we could without getting too close to -1 volt. You know, again, -1.5, maybe not quite as linear as we want, not as, you know, much voltage swing, or as even of a voltage swing as we would hope for, but it's a compromise. And so we went up with, minus 1.25 volts, and we came over and found that that put us at 0.8 milliamps. So the next part of the equation was using that to come up with our bias resistor. So we were at 750 here, but remember originally we had 1600 ohms, but since both of these cathodes are sharing That resistor, we cut that in half to 750. We could have also went up to 820. Something between 750 to 820 would have been a good place. Now for the tail resistor, we kind of went backwards. We took the 0.8 milliamps and multiplied that by 2 to get 1.6 milliamps. Then we divided our 50 volts divided by 1.6 milliamps, so 0.0016, and that's where we came up with something in the neighborhood of 31,000. So we just transferred that to a close standard value of 33K. So watch this video as many times as you want to. What I'm going to do is link down in the description to Aiken Amplifier's website to this particular topic. They don't use the same tube here, but it's the same logic in the math. But don't take my word for it. Just go to the website and get some solid info. But I always appreciate it whenever you guys stop by, and keep an eye out for the next one. Thanks.